Excellent. Quick question. How many people have actually seen the aurora? Excellent. So we're in good company then, so quite a few people. What I'd like to do is give a little explanation as to what the aurora is and how it occurs. And then I got back from Iceland on Thursday, so I'll show you a few of the pictures that I took over the week before I got back on that particular day. Now, any lecture about astronomy and aurora in particular could get very, very... oh, we need to switch the thing across. Come on. You can't get the staff. That's better. Yeah, any sort of lecture that deals with astronomy or aurora in particular could get very, very complicated. And if we were to do this mathematically, you'd probably fall asleep within 2 minutes. Now, we know that astronomy is a very visual subject, so you'd be pleased to know no more equations. The rest of it is going to be pictures and writing. Now, what are the northern lights? Well, they're this phenomena that occurs in polar regions that appears to give us wisps and luminous arches of light. And very often people, get very confused because they see these things in the sky and think, oh, it's a little bit cloudy or something like that. But when they begin to sort of perceive the colours, they then realise that they are seeing something that's really, really special. Now, aurora is the Latin word for dawn, and boreas, of course, is the word pertaining to the north, which is where we get the name the aurora borealis, the northern dawn, or we get the aurora australis, the southern dawn. The reason the aurora borealis is better known is because it covers a greater populated area in the northern hemisphere than it does in the south. If there's a very strong sort of display in the south, it might extend towards New Zealand and Australia, but essentially Antarctica is the region, whereas in the north, of course, we cover Canada, Russia, all the Scandinavian countries, so we a lot more people get to see it. And to the Romans, Aurora was the goddess of the dawn. Now, we have to talk about the sun really in order to explain the aurora and what caused it, because without the sun, there really wouldn't be any aurora at all. And the reason we talk about it is because, the sun is an ordinary star. Fortunately for us, it's not a supergiant star like Antares or Betelgeuse. And because of that, it's more efficient at using its fuel. So luckily for us, it's going to last for many, many billions of years. Now, if we take it in context about the size, we can say that the sun, we could fit 1 million Earths inside it, which is pretty big, and some of the energy from the sun that is emitted comes towards us down here on the Earth. Now, the sun loses about 4 million tons of itself as energy every single second of its life. Now, if we could convert that kind of energy into electricity, again, an example, if you imagine how big Europe is, just 1 second's worth of that power from the sun would keep Europe in electricity, for example, for about the next 80,000 years. So we know the sun is very, very energetic, and some of those energetic particles do come towards us. Now, here's a real-time image of the sun taken by a satellite, and we can see on here we've got these prominences and flares that are erupting from the surface. And inside the sun, the main area of interest is the core. That's where all the action is. This is this nuclear reactor where hydrogen is being turned into helium, and the byproduct of that is lots of energy and heat. Then we have the shell, and we've worked out it takes about 1 million years for energy to propagate through the shell to what we call the photosphere, which is this bit that we get covered when there's an eclipse, and by that time it's had chance to sort of cool down. So the core 15 million, the outer surface, the photosphere, about 6,000 degrees. Inside the sun at the moment, we have a state of what we call hydrostatic equilibrium. And what that means is that the nuclear pressure pushing outwards is being counteracted by gravity pushing inwards, and the sun will merrily just go on doing its thing. Ultimately, though, of course, the hydrogen will run out, the sun will get squeezed inwards, and then that helium will then start to expand outwards. But there is something odd about the sun as well. On the Earth, we just say the Earth revolves around every 24 hours. So it doesn't matter where you live, 24 hours is about what we call a day. The sun is slightly different in that at the equator, the equatorial region, it rotates around in 25 days. At the poles, it rotates around in 35 days. So there's a 10-day difference between the middle of the sun and the poles, and that's called differential rotation. And because of that differential rotation, the sun gets very, very distorted and its magnetic field gets very, very twisted. Now, when that magnetic field gets twisted, it leads to the formation of things like sunspots. And again, sunspots are sort of the key to Aurora as well, because they all occur within this equatorial region. They generally come in a pair, and they affect the magnetic field lines that we've said get distorted. Now, when that magnetic field breaks free from these sunspots, that's when this energy gets emitted towards us. In fact, this last week, there's been a couple of flares that have come earthwards, which is probably what I was looking at on Thursday and Wednesday and Thursday night. Now, we said that the sunspots are cooler regions of the sun, but something is stopping the energy getting to the surface, and that is the magnetic field. And there's a little example of what's going on, that the energy is stopped. But again, it does break free. On the left, we'll see an animation of a sunspot, and that sunspot there is actually about 3 times bigger than the Earth. So these things are very, very big, and they do emit a hell of a lot of energy. Now, we also have this thing called the sunspot cycle, and people have worked out that the sunspot cycle is 11 and 22 years, where it tends to sort of repeat itself. And we're actually at the moment meant to be, well, last year, in fact, in solar maximum, when we had the most activity of the sun during this particular cycle. But for whatever reason, the sun was not very active, and it's starting to get active now. So we reckon the best auroras will possibly be visible this year, next year, maybe extending into a year after. But certainly there's going to be activity going on. Sunspots all occur in this band, as I say, 30 degrees of the equator, but sometimes we have periods where there aren't any sunspots at all, and one of the famous ones was this thing, the Maunder minimum, between 1645 and 1715, where hardly any sunspots occurred at all. We don't see many records of aurora at that time, and this is this thing where people are believing there could be a link between solar activity, the amount of radiation, and climate, because during that period of the Maunder minimum was when places like the River Thames in London were actually freezing over. So we'd got very cold temperatures, hence this link to climate, and a lack of aurora in the sky. It was only when the sunspots built up again that we saw them. And here's an example, solar minimum on the right, going round to solar maximum on the left. The idea is that the more sunspots there are, the more solar activity, the greater amount of aurora that you will actually see. And we can plot that on a graph, this famous thing called the butterfly diagram, which we can then predict when the next sunspot numbers are going to be high again. Now, the prominences, where these sunspots have an effect where the energy breaks free, the sun's doing this all the time, but the majority of it is facing away from us or at an angle, so we actually miss what's going on. But there are, from time to time, these solar flares that actually do come towards us, and they're the ones that emit these protons and electrons that interact with the Earth's magnetic field, and that gives rise to the phenomena. I've got a few, 3 videos here to show you the sun is spewing all this material out, this solar plasma full of electrons and protons. And here's another one. But in particular, when these energetic particles come towards the Earth, they have to be careful, especially with satellites in orbit, because they can affect communications. And it has been known in the past where communications have been affected in the ionosphere with signals. And in fact, in Canada, many years ago, there was a power outage where a substation was affected, and it blew the substation to pieces. And again, if you're a business that is interested in satellite communications and you've just spent $10 billion developing a satellite and launching it, the last thing you want is a flare like that and all the material coming towards it, because it's not going to be any use. So there's a lot of things now, space weather prediction, telling companies when to turn their spacecraft away from these particularly damaging flares. The Earth is protected by its own magnetic field. And our magnetic field, if we go back to school, I remember when I was in school, we did an experiment in school where we had a bar magnet, north and south, a piece of paper on top, and then we sprinkle the iron filings on it. It's an experiment that most people do, and you get this shape of the butterfly, the sort of bow shocks around it, which is essentially what we have around the Earth. But the solar wind, what happens is, when it's erupted from the sun, it comes towards us, takes about 2 to 4 days typically to do that, unless, many years ago we had the Carrington event where energy came from the sun in 19 hours, which was very exceptional. But generally 2 to 4 days, and it comes towards us and then begins to interact with our magnetic field. And what happens is that the solar wind hits the bow of the Earth, it channels the particles behind the Earth where they reconnect, and then they bounce back, and the magnetic field is weak at the north and south pole, and that's where these particles enter the atmosphere and start to interact with the gases in our atmosphere. High up, the altitude typically in the ionosphere, 95 to about 110 kilometers, it has been known in the past for them to be much higher than that. And for example, when the space shuttle was flying, the space shuttle would actually fly through auroral displays. And in fact, on the International Space Station, as you see later, they have a camera on board now. And when they're flying over polar regions, they always video what's actually going on there. But what we're trying to say is these aurora occur very, very high in the atmosphere. But when you're looking at them, you can look down and you think, oh, I could almost touch them, but they are occurring very, very high, much higher than the mountains that we have down here on the Earth. Now, in the atmosphere, of course, we've got oxygen and nitrogen primarily. Atomic oxygen is one atom of oxygen surrounded by 8 electrons. The molecular oxygen, the O2 that we breathe in, is 16 electrons, and then the atomic nitrogen is 7 electrons. And what happens is the electrons from the solar wind, they join on to one of these orbits. So the atomic oxygen gets 9 electrons, the molecular oxygen will get 17 electrons, and the nitrogen will get 8, and the result of that is they give off a photon of light as energy, and depending where they are in the atmosphere, that dictates what color that is. So essentially green is the predominant color because we have more molecular oxygen than we have atomic oxygen. Atomic oxygen tends to give off a sort of a reddy color, and nitrogen gives off a sort of a pinky color as well. So it's all to do with how they release that energy once they gain that electron. Now, high up in the atmosphere, of course, where we get the atomic oxygen, it takes longer for that light to be emitted, and there's less of it, so it takes longer and it's more difficult to see. Whereas down a bit lower down where the molecular oxygen is, it releases energy quicker and there's more of it, so it gives off a brighter green. So if you ever see the aurora and you'll see pictures, the main color that you see is green. It's all to do with this fact that they're gaining electrons and giving off this photon of light. Green is the predominant color. I've had people say they've seen white, they've seen violet, they've seen orange, colors like that, and I'm not going to tell them they haven't because everybody's eyes are slightly different. But to me, green is the color that I've mainly seen. But the other thing, of course, is when you're looking at the aurora, is the angle at which you view the display will also have an effect on how you see it in the sky. So if you're looking perpendicular to where the atoms are hitting the upper atmosphere and the ionosphere, then you'll see point B, where you'll see the classic curtain shape going across. But any slight angle to that, you will see like an arc curving around, or you'll see a band. So there are lots and lots of different forms within an auroral display, and you can see several of them all in the same display as they move around. People often ask, when I see a picture, do I see that with my eyes? When the sun is active, yes, you do see that with your eyes. You can literally see the movement across the sky like this. When it's a little bit dimmer, of course, the camera is always going to be more sensitive to you than your eye will be. And one of the things I try to do with the groups I take to Iceland is I try to get them to set their cameras up before we go outside and give everybody the opportunity to, taking a picture themselves, because it's great looking at pictures online. There's nothing like the satisfaction, as we all know as astronomers, of taking your first picture of something astronomical, and it's that satisfaction that we try to give people. Now the causes, the ideas, what caused the aurora, one of the first guys to sort of come up with an idea was Edmund Halley, of course, famous for his comet, and he was one of the first people to reckon it must be something to do with the magnetic field lines in the Earth's atmosphere, but he wasn't quite sure the mechanism that caused them. And then some people, of course, reckon Galileo was the first person to actually coin the phrase aurora borealis. Again, there's no real written record of that, but certainly he was one of the people that would have seen it. And then he wouldn't have known really about this thing called the auroral oval. Now the oval is a zone of activity which is where you need to put yourself in order to see the lights properly. Now, when the auroral oval extends from the poles, it can extend a few thousand kilometres, which is why people have seen aurora in the Lake District, in sort of northern Scotland. They've had some fantastic displays recently, but when the activity is a bit less, it shrinks. So what you need to do is put yourself in Scandinavia or in Canada or Alaska, and then you should be around where that auroral oval is. And what you do is you go out between between what we call 10 and 2 a.m. is what we call Geomagnetic Midnight, which is where your location rotates into the thickest part of the oval, and that's when you should essentially see the aurora. But we've seen it as early as 8 o'clock in the evening and as late as 5 o'clock in the morning. So, you know, there's no real way to predict what it's going to be. You might see it for 2 minutes, you might see it for 5 hours. It just depends on what the activity is like. There is a measure of probability of aurora, that's called the KP index, which is the measure of energy in the ionosphere in the east to west. But it goes from 0 to 9, the KP index, and when it's been a 0 in Iceland, we've seen aurora. So I cannot imagine what it's like when it's a 9. It must be like daylight. So it's an average measure, so we tend to take the notice of it on the trips because, you know, as I say, well, I've been there and seen aurora when it's meant to have been no chance at all, and we have seen it. Now, the myths and legends then. Are aurora good luck or good fortune? Well, there are many legends, and they are very, very varied, and we've got many, many records, fortunately, to tell us about them. But Hesiod in Greece actually mentioned blazing skies, which shows you that when he was around, less light pollution, there must have been a lot of solar activity around because he was seeing aurora down in Greece. They have been recorded as far south as the equator before now. Aristotle mentions shining clouds, and Knut Hansen, an Icelandic poet, he mentions the lights as being this heavenly feast. But the existence of the Aurora Australis, the southern lights, wasn't really known about until people like James Cook went into the southern hemisphere sailing, and they were the first people to really see the southern lights. And the southern lights is a mirror image of what is visible in the north. We see in Central Europe in the Middle Ages, they reckon that the aurora that they saw was a sign that they were going to be not blessed with anything good. It was all going to be doom and calamity. It was going to be illness and plague and death. And when aurora was seen in southern Europe, especially the red, they likened it to the blood of battle. So all these many different things. Some people reckoned it was candles in the sky that were on the clouds and giving off the different lights that were visible. In Bamberg, in Germany, they reckoned that it was people seeing flashing lights. Must have been superstitious because not everybody saw that kind of thing. In Scotland, the aurora is called the Merry Dancers. And the merry dancers, if they move quickly, then the weather is going to be unsettled, and if they slow down, then the weather's going to be a lot better. A lot of legends are associated with weather or harvest and things like that. And the Greeks and Romans reckoned they could see these aurora, and they called it chasmata. In Scandinavia, one legend is they call it Silsblixt, which is actually the reflection of light from the herring shoals in the sea, where they reckon the light hits the fish and it bounces into the sky. And if you're a fisherman and you saw this light in the sky, you would think, there's all the fish, I'm going to go and catch all the herring and we'll have a bountiful catch. One example. Another one is that people thought that during the day, the glaciers in the polar regions absorbed energy, and then they emitted that energy at night from the ice. And again, we saw the northern lights in the sky. We know that not to be true. This is another one from Scandinavia, where two swans have a competition to fly north, and it gets so cold they get frozen into the ice, and it's only when they start to fly off and they break loose and their wings are flapping that they then begin to see the aurora as a display. In Finland, they call it Ravontulet, which is the Arctic fox, and it's as if the fox is running across the sky, and its tail is giving sparks off up into the sky. The Copper Eskimos of Canada, again, if they saw good aurora, they reckoned it was going to be bountiful hunting, and people would have a good harvest. In China and Japan, and we do see a lot of Japanese couples in Iceland, where they reckon that if they conceive a child under the northern lights, then that child is bound to be prosperous and be blessed with good luck in the future. Now, given how cold it gets in countries like Iceland, it's not something I recommend trying to do, because it would be pretty cold. In China, where they saw them, they reckoned it was a fire-breathing dragon, much like when they see an eclipse, they think the dragon is eating the thing. And this is one not to be recommended from Alaska, where the Inuit say to calm the aurora down, it's a good idea to throw urine and dog poo at it. So not a good plan. Don't be doing that, especially if you go on any wonderful trips. The Asquilicuat Inuit, they reckon it's a game of football where the souls of the dead are playing football with the head of a walrus, and the idea is to kick the walrus skull, and when the tusks land in the ice, then it gives off the sparks and gives off the beautiful things. The Aboriginal people had ideas of whistling at the Aurora to give off, to ward off the spirits. Some people reckon they can hear the Aurora, and I was speaking to somebody just last week who reckoned they'd heard them in the past. Never heard them, but again, some people do believe you can hear them. And again, another theory is that it could be the icebergs in the sort of northern seas crashing together, again, which have the result of giving off the lights. If you ever do go to Iceland, they say there that if a pregnant woman looks up at the sky, her child is sure to be cross-eyed. And believe me, I've spent many an hour in Reykjavik looking for cross-eyed children and never seen them. So they must not do that. They must keep them indoors when they're pregnant. Here's a video from the International Space Station of an auroral display they saw. You can see from space the red is more predominant because you're higher up than we are. So we'd be seeing through the green into the red. They see the red down into the green, which is quite an impressive thing. And now with the big window on Cupola, they get to see them a lot better. Must be an amazing sight from orbit to see something as good as that. And what I'm going to do now is I'm just going to show you a few of the pictures, some of the ones I took just last week, and then I'll show you a few that I took a little bit ago in March. Could you just switch that big light off, and then I should be able to see them a bit better. And I'll just run a few of them in. Again, if anybody's got any questions about anything later, just come and see me. This was on Wednesday evening, where I managed to get, it's difficult to see on that, it's much clearer on screen. There's a Taurid fireball that went straight through Taurus, and I managed to capture that. And this, as you can see, this is on the outskirts of Reykjavik, where there is a little bit of light pollution, but look how, the Aurora was still easily visible. This is looking above, straight above. This is this Casmata that the Romans reckoned. This is with the hotel where we stay, but we turn all these lights off so we get a much better view of the fainter stuff. And even with a bit of cloud in the sky, it really adds to the sort of experience that we see. This is overlooking a lake where we actually, if they get a good display, you get the Aurora reflected in the water. And then an auroral arc. This was an amazing sight to see this, a perfect auroral oval, which was probably about 200 miles distant, but we managed to see the whole thing from one side of the sky across to the other. It really is just an incredible thing to see when it's active. That was a car that came across the horizon, middle of nowhere. It's my close encounters shot, that one. And then, it's always sometimes nice to get things in the picture as well, just to give it a bit of perspective and other close encounters. And this was a display in March where we had different forms. So we had rays, arcs, and curtains all in the same display. And it just got better and better from there. So that's the kind of thing that you can see by going 2.5 hours north, or a few hours further into Scandinavia, into Finland, or anywhere like that. And there's the tour company that are here today. They're running the tours as well. So go and have a look at the brochures. And if anybody wants any details of the ones that I'm currently involved with, then please come and ask, and I'll give you all the information that you need. But thank you for your attention, and good luck Aurora hunting. Keep going.